Okay, pre-calculus, we are starting Unit 7, Discrete Mathematics. So, it sounds pretty intimidating, but it's not very bad. You'll be okay with it. So anyhow, here we are on Lesson 1. Your basic goal for the lesson. Hold on, I'm trying to see why these, there we go. Okay. Your basic goal for the lesson is to learn how to count. Not 1, 2, 3, but to count the number of ways in which a scenario can occur. So, example 1. To make a yogurt parfait, you choose one flavor of yogurt, one fruit topping, and one nut topping. How many parfait choices are there? So you can see from the table, there's 2 yogurt choices. There we go. There's 2 yogurt choices. There is 5 fruit choices, and there are 3 nut choices. So the most basic way to solve this problem is to make a tree diagram, which would look something like this. You can choose either chocolate or vanilla. Those are 2 yogurt choices. And then after you choose your chocolate or vanilla, you have 5 choices. 1, 2, 3, 4, 5. So we have peaches, strawberries, bananas, raspberries, or blueberries. And then the same thing goes here. 1, 2, 3, 4, 5. Peaches, strawberries, bananas, raspberries, blueberries. And then after you choose all your fruit, or which fruit you want, then you can choose your nut option. So for those, again, there's 3. So each one of these gets another 3. All right, and we can have almonds, peanuts, walnuts, almonds, peanuts, walnuts, almonds, peanuts, walnuts, almonds, peanuts, walnuts, almonds, peanuts, walnuts. And then the same goes here. 1, 2, 3, almonds, peanuts, walnuts, almonds, peanuts, walnuts, almonds, peanuts, walnuts, almonds, peanuts, walnuts, almonds, peanuts, walnuts. So that would be a tree diagram that shows all the different options. And so when it says how many parfait choices are there, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 choices. There you go. But luckily, there's a better way, although the tree diagram will work for you. So you are welcome to use that if you like, but you also need to know the fundamental counting principle. And this says if there are n items and m1 ways to choose the first item, m2 ways to choose the second item after the first item has been chosen, and so on, then there are, this should say m1 times m2 times ... up to mn. So you're just multiplying all those numbers, ways to choose n items. So in this situation, the problem above, there were 2 yogurts, so M1 would be 2. There were 5 fruit options, so M2 would be 5. And then there were 3 nut options, so that would be our third number, and we multiply those and we get 30. A little bit easier than the tree diagram. You need to know the fundamental counting principle. It will sometimes be shortened to CP, just so you're aware. Okay, so basically the fundamental counting principle says that if you have multiple tasks to accomplish and each task has a different number of ways it can be done, then the total number of ways to accomplish all of the tasks is found by multiplying the number of ways each task can be done, which is what we just did. Although we weren't talking about tasks, we were talking about ice cream, which is way better. Okay, example 2. We have a password for a site. It consists of 4 digits followed by 2 letters. The letters A and Z are not used, and each digit or letter may be used more than once. How many unique passwords are possible? All right, so I'm going to put a line through here because we're going to do the problem again a different way. So the first way, though, we're going to say, okay, we have 4 digits. So that means I have a digit, 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 and then I need a letter, 2 of those. And just to review, a digit is any digit from 0 through 9. And so there are 10 digits each time. So I have 10 options here, times 10 options here, times 10 options there, times 10 options there. And then how many letters are there? Well, there is 26 letters, but 2 letters cannot be used. So that takes us down to 24 times 24. Yeah, and notice in the question, it says each digit or letter may be used more than once. That's pretty important. And so just keep that in mind. But anyhow, so here we are using the fundamental counting principle, and we are going to use our calculator, and we're going to go 10 times 10 times 10 times 10 times 24 times 24, and you should get an answer of 5,760,000 passwords. There are that many different combinations. But like I said, I want to do this problem twice because now I want to change it just a little bit, and I want to say they may not be used twice. May not be used, my goodness, twice. So in that case, for the first digit, how many options do I have? 10. But for the second digit, I've already used one of those digits, so now I only have 9 options left. For the third digit, there's only 8 options left, and for the fourth digit, there's only 7 options left. So saying this changes the problem just a bit, right? And then for the letters, the first letter, there's 24 letters available. But the second letter, I've already used one of those letters, so now there's only 23 available. And for this one, you're multiplying different numbers, you're going to get a smaller value. I don't have that in my notes. Let me do it real quick. So I have 10 times 9 times 8 times 7 times 24 times 23, and I get 2,782,000. Yeah, wait a minute. 782, okay, 080, there we go, passwords. Okay, so moving on, example 3. How many ways can a student government select a president, a vice president, secretary, and a treasurer from a group of 6 people? So in this problem, you need to note that, well, let's just make the rule that you cannot be president and vice president, etc. at one time, at once. So we need 6 or 4 different people. One person cannot hold more than one position. So how would we set this up using the fundamental counting principle? Well, we would say, all right, first let's do our president, and there's 6 options for president. Then let's do our vice president. And once we have one person as president, now there's only 5 people left, so that would be 5. And then what else do we have? Secretary, well, we've already used 2 people, so now we have 4 left. And then finally we have treasurer, and there's only 3 left. So you multiply 6 times 5 times 4 times 3, and you get 360 different student governments with only 6 people. Pretty amazing. Okay, next page. All right, a factorial. The product of the natural numbers less than or equal to the number. So first of all, please remember, whoa, hold on. I think I can stretch that back out, I hope. Yep. Okay, first remember that a natural number does not include 0. Zero is not a part of the natural number set. It is a part of the whole number set, but it's not a part of the natural number set. So make sure you don't include 0 in this, because if you do, you've zeroed everything out. It's expressed, a factorial is expressed using an exclamation point. And this is very important. 0 factorial equals 1. That's just the way it is. So make sure you know that. So when it says evaluate 5 factorial, what this means is it is the product of all the natural numbers less than or equal to the number. So 5 factorial means 5 times 4 times 3 times 2 times 1. And you multiply all that out and you get 120. And right there you can see why we are not including 0, because if I put a 0 in there, factorials would always equal 0. So do not include 0. Now a cool little thing here, if you go to your calculators and you find the math button, and let's see, you move to the right to the prob column, and then I think the factorial is like number 4. Let me pull it up real quick. I should have had that ready, but I don't. Come on, baby, open up. Oh, it's been too long. I have to do a new sample, and I don't have time for that right now. So, yes, we want to quit this. All right. But anyhow, if you go, you hit math, you move your cursor over to problem, and yes, factorial is number 4. And you'll see that in there. And when you use your factorial, so if you want to do 5 factorial, then first thing in your calculator is, type in a 5, and then you go to here and you type in your factorial, and it will give you an answer. So you'll get good at that, and if you don't get it, we'll do it in class. Okay, factorials are used when you want to arrange or order every item in a set. So whenever you're going to use every item, you can use a factorial. Example 5, how many ways can you arrange 7 pictures on a wall when you have 7 to choose from? So obviously we're using all 7 of the pictures that are available to us. So therefore, since we're going to use all of them, we can do 7 factorial. And you can practice that on your calculator, and you will get 5,040 different arrangements. Okay, permutations with reruns. Technically, these permutations, well, we'll go ahead. By the way, another word for a factorial, because we're going to come across this word permutation, and then later on we're going to come across a word called a combination. And a factorial is a permutation. And along with the fundamental counting principle is also a permutation. So just keep that in mind. Combinations are a little bit different. Very similar, but a little different. So anyhow, okay. So we're going to do a permutation with a rerun. And let's look at example 6 here. What this means is how many ways can I arrange the letters in guitar? Now when you look at that, we're not trying to make words, we're just trying to arrange the letters in different ways. There are 6 letters, 1, 2, 3, 4, 5, 6, so 6 letters. And we want to use all the letters. So therefore, we would use a factorial. And you do 6 factorial, and you find out that there are 720 ways to arrange those letters. Now, those ways will not make words, but they are different ways to arrange the letters. Going on to example 7. How many ways can we arrange the letters in the word England? So again, you count and you see you have 7 letters, but the problem is that the N is a repeat letter. And so since N repeats 2 times, like every time it arranges, like if you put this in a computer program and it arranged these letters in different ways, there's no way to it doesn't matter which N is which N. And so what we have to do is we have to divide out that repeat. So then what we're going to do is we're going to say, all right, since this has 2 repeats, we do 7 factorial, but then we have to divide out what repeats, which is one letter 2 times. So that would be a 2 factorial. Which leaves us with, and you can set this up in your calculator, but you could also just write it out a little bit. All right, and then that's divided by 2 times 1. So these all factor out. So really all we're multiplying is the 76543. But anyhow, put this in your calculator and you get an answer of 2,050 ways to repeat or to arrange these letters. Just remember that when you have a repeat in a letter, you have to divide it out. That's what it means here with reruns. Okay, example 8. So same problem, but this time we're looking at the word Mississippi. So we count the letters. I think there's 11 letters, but there's a lot of repeats. So we're going to set this up. We have the I repeating 4 times. We have the S repeating 4 times. We have the P repeating 2 times. So therefore we set this up as 11 factorial divided by, we need a 4 factorial taken out for the I, another 4 factorial taken out for the S, and then a 2 factorial taken out. And you set that up, put it in your calculator, you get 34,650 ways to arrange those letters. Okay, so anyhow, that is, make sure you know how to do this. I know this shows up on a quiz or a test or something like that. Okay, permutations. A permutation is a selection of a group of objects in which order is important, and you are not using every item in a set. So I told you up here that a factorial and the counting principle falls kind of under a permutation. The difference is that in a factorial you are using every number in a set. And so here is how we set up our permutation. N stands for the number of possible. I think we did this a bit last year. R stands for the number to use or choose. Okay. And just keep in mind, again, you're going to find this, I'll show you where this is in your calculator if you haven't found it already, but you will, for every problem, have to write this up with, of course, the right numbers. And then you'll be able to use your calculator. But you have to always show me this little fraction here. So, because the more you show it to me, the more you will know it. And then, that's what we want you to do, is know it, not just depend on your calculator. Okay, so permutations can be found on your calculator by pressing the math and then PRB, and then instead of going down to the factorial, which is number 4, I think this is the second one, let me check. It's number 2, at least on my calculator, probably on yours too. Okay, so on your calculator right now, so when you do a permutation, the first thing you do is the calculator portion where you find the permutation in your calculator, and then you put in the 8 and the 3. And remember though, anytime you're going to do this, you're going to write it out. So this would be 8 factorial divided by 8 minus 3 factorial. That's what your permutation is. So make sure you write this down, this little fraction, then use your calculator. And you will get 336 ways. Looking at what this is, it's 8 times 7 times 6 times 5 factorial, right? We keep going down from 5. Here, 8 minus 3 is 5 factorial. Those cancel. So technically, we're doing 8 times 7 times 6, and you get 336 ways. Example 10. How many ways can a student government select a president, vice president, secretary, and a treasurer from a group of 15 people? So when you are doing these, the question you need to ask is, does order matter? Because down here we're going to talk about a combination where order does not matter. But a permutation, is when order does matter. And so it does matter, like who is president, who is vice president, who is secretary, and who is treasurer. For example, if I say, Joe, Sam, Andy, and Ellie are, the president, vice president, secretary, and treasurer, but I don't know which one is which, well, then that's not very helpful. So technically, the order of these names would matter. Like in this order, here's president, here's vice president, here's secretary, here's treasurer. Well, another group using the exact same names could be Joe, Andy, Sam, Ellie. In which case, Andy is now VP and Sam is secretary. And so the order that I come up with for these names counts because there's a difference and we want to know who is who. And so that's what we mean when we say order matters. The order is important. Therefore, it is a permutation. And so to set this up, you're just going to write, all right, it's a permutation. There are 15 people to choose from, and there are 4 choices to be made. And there is the setup for the permutation. Then you are going to always write this, 15 factorial over 15 minus 4 factorial, and then you're going to take out your calculator, put those numbers in, and you find out that there are 32,760 ways to come up with the president, vice president, secretary, and treasurer out of a group of 15 people. Okay, moving on. Oh, by the way, just to point out, this problem, this is how you see that those counting principles the same as permutation. Remember, this is exactly the same as a previous problem, number 3. Previous example on the previous page, but we only had 6 students. And so you could use the counting principle for this as well. Okay? All right, moving on to combinations. So a combination is a selection of a group of objects in which order does not matter. Order is not important and you are not using every item in the set. Here is your formula. Again, N stands for the number of possible. And R stands for the number to use. Again, this is also in your calculator. I think it's right down from a permutation. So let's see. Yep, it's number 3. So you do math, go to prob, and then number 3 to get your combination. Let's see. Oh, I do want to point out one thing here, that there are fewer combinations than, I should write the word usually, just to keep all things safe. Fewer combinations than permutations. Why is that? All right, well, let's look at my little example up there. I was using my 4 kids for president, vice president, secretary, and treasurer. Joe, Sam, Andy, and Ellie. Okay, so this is a combination. Joe, Sam, Andy, Ellie. We don't care the order. We don't care which one comes first or where they come in the set. This is a combination. Whereas a permutation would be, okay, one is Joe, Sam, I shouldn't write it, Joe, Sam, Andy, Ellie. The next one is Joe, Andy, Ellie, Sam. The next one is Joe, I've lost track, Ellie, Andy, Sam. The next one is Sam, Andy, Ellie, Joe, and so on. You can see how that goes on. There's a whole bunch of options there. But these are permutations because the order of each one matters. This is the combination. So here we have one combination, but a lot more permutations. Okay? In fact, how many permutations would there be? 4 factorial, which is 4 times 3 times 2, which is 24 different options here, and only one option for a combination. All right. Example 11, using your calculator here. I want you to find the combination in 11, but please remember before you do that, you need to write it out. So you're going to say 8 factorial, 8 minus 3 factorial. Notice that portion is exactly like a permutation, but then we do an extra little division there of 3 factorial. Make sure you write this fraction every time. Writing it out, it would be 8 times 7 times 6 times 5 factorial divided by 8 minus 3 is 5 factorial times 3 times 2 times 1. So these cancel. The 2 can cancel with the 8. So these are doable, you know, if you want to without that lovely key in your calculator. But anyhow, you get 56 ways. All right, so example 12. There are 12 different colored cubes in a bag. You want to know how many ways Randall can draw a set of 4 cubes from the bag. So in this case, there doesn't seem to be any reason to care what order the cubes are, right? Order does not matter in this problem. All we want here is a set of 4 cubes. We're not looking for anything more special than that. So order doesn't matter, therefore it's a combination. So setting that up, we say, well, it's a combination. There's 12 options, and we want 4. So there it is. It's all set up. Then you're going to write it out for me. So you have 12 factorial over 12 minus 4 factorial divided again by 4 factorial. Stick it in your calculator, and you get 495 different sets are available, or different ways, whatever you want. Okay, example 13. And this is where the tricky part comes in because, you know, finding a permutation or a combination is not difficult. The trick is knowing which one to do. So example 13, for each scenario, determine whether factorials, permutations, or combinations can be used, then find the answer. And along with this list of factorials, permutations, combinations, don't forget about the counting principle as well. Okay. So Nathan has a dozen eggs. He wants to decorate 5 eggs for an art project. So he can use any eggs. It doesn't matter the order of the eggs. Order doesn't matter. So therefore, it is a combination. So we're going to say a combination. There's a dozen, so that's 12. He's using 5, and so we're all set up. To keep your teacher happy, you're going to write 12 minus 5 factorial times 5 factorial. Then you can use your calculator, and you get 792 sets of eggs. Next one, B. Mr. Gunther is lining up 12 kindergarten students for a performance. All right, well, Mr. Gunther would get fired if he only lined up 11 of them and stuck one in the corner, right? So he's going to use all of the students in his line. Therefore, it's a factorial. He's using all students. So technically, we would say 12 factorial, which you can put in your calculator, and you find out that there are 479,001,000 different ways he could line up the students. But I want to show you why I say that a factorial is also a permutation, because if I would set this up as a permutation, and I say, okay, it's a permutation, there's 12 students, he's using all 12, right? Well, using what we know about permutations, this would be 12 factorial divided by 12 minus 12 factorial, which is 12 factorial divided by 0 factorial. And remember that very first thing I said is that 0 factorial equals 1 by definition. So this is 12 factorial divided by 1, and there we are right here. And so if you use a permutation on this instead of a factorial, that's fine because you get the exact same answer. Next, C. Rachel has 10 valuable baseball cards. She wants to select 2 of them to sell online. All right. So the cards might be valuable, but it doesn't matter. Like, let's say, you know, she has 12 cards. We'll just say a few of them are here. A, B, C, D. There's 12 of those. All right, let's say these are the valuable ones. But if she says, like, if you have this order, I'll sell A and B, or I'll sell B and A, it doesn't matter which one, you know, comes first in the set. And so, therefore, the order does not matter. And it's a combination. And so you would say C, there's 10 of them, she wants 2 of them, and then you would write it out, 10 factorial, 10 minus 2 factorial times 2 factorial, stick it in your calculator, and there are 45 sets of 2 cards that she could sell. All right, D, Don has 5 soccer trophies he can line up on the mantle of his fireplace, but he only has room for 4. Okay. The idea of lining something up is that, you know, you would put your most important one first, and then the second most important one, and the third most important one. And so that says that order matters. And so therefore we would say it's a permutation. That those words lining up, you know, you're not going to start with your worst trophy. You're going to line them up. There's an important order there. That's what lining up means to me. So, okay, we're going to call it a permutation, and there's 5 trophies. We're choosing 4, so we're going to say that's 5 over 5 minus 4 factorial. Put it in your calculator, and there's 120 ways to line up those trophies. E. Bree has to select 5 photos from a box containing 25 photos to use in the yearbook. So again, some pictures are going to be better than other pictures, but that's not the question. The question is, does the order of the 5 pictures sitting on her desk that she is going to collect, does that order matter? And no, that order does not matter. I mean, if I have my 5 favorite pictures, 1, 2, 3, 4, 5, I don't care which order they're in. I'm just getting those 5 pictures together. So it's a combination. There's 25 pictures. She's choosing 5. And you're going to write 25 factorial, 25 minus 3 factorial, and then you'll get your answer of 53,130 possible groupings of pictures. And that is the end of the lesson.